Welcome back. Hopefully you made it through the dispersion forces one. It's probably the most complex of visually trying to explain it. And if you don't have that under control at the moment, make sure to you annotate a couple of questions on what's confusing you, and we'll go through them in class tomorrow. So moving on to our next type of intermolecular bonding, we're going to have dipole-dipole bonding. So hopefully this sort of instinctively makes you think of polar molecules. Okay, because remember, in a polar molecule, we have a permanent dipole. Okay, we must have permanent dipoles. Okay, so permanent I can't spell. Okay, so we've got a permanent dipole, which is distributed around our central atom non-symmetrically. Okay, so dipole-dipole bonds occur between polar molecules only. They have to be polar. Okay, so we're talking about molecules like CH3Cl. Okay, so chloromethane, where we have the chlorate, we've got 3 chlorines coming off. Oops, let's go CH3, change that, 3 hydrogens and a chlorine. So the CHCl3 would also be polar. Okay, but this is going to be a delta minus, delta plus. We're going to have an overall dipole in this molecule. So we're talking about molecules that have this kind of influence. Okay, so they have to be polar molecules. And then we're talking about the interaction between the dipoles, so those sides that we've set up in the molecule. So we have something that's slightly positive and slightly negative. So those slightly positive and negative charges will attract each other, whereas if we put the 2 slightly positive ends together, they will repel each other, as we can see in this diagram here. So here we have repulsion and we have attraction between the oppositely charged ones here and here, whereas we've got repulsion here and here. So this here is going to be a dipole-dipole interaction, okay, or dipole-dipole bond. And it is a type of intermolecular force, okay? So these are stronger than dispersion forces, which means that any polar molecules that have these, we could expect them to be starting to exhibit for similar sizes higher boiling or melting points, okay? And this diagram here is showing us our positive and negative and how they would arise. Okay, so some examples of this are things like our HCl. So we can see these dashed lines here always give us intermolecular, okay, and then the strong lines are our intramolecular, okay, in this case our covalent bonds, and our dipole-dipole attractions here. In SH2, remembering we've got 2 lone pairs on our sulfurs here, so we have delta plus and delta minus. This dashed bond again is showing a dipole-dipole attraction between these partially positive and partially negative dipoles. So that's dipole-dipole. Any polar molecule that has a permanent dipole, which is all polar molecules, will have dipole-dipole attraction. Okay, there is the third type that we said we needed to cover though, which was hydrogen bonding. Now, hydrogen bonding is a special case of dipole-dipole. Okay, and essentially this special case is because the electronegativity difference is so high that we get much stronger bonds. So these ones are hydrogen bonds, okay, that occur between polar molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen, okay, and Miss Greenwood-Smith has pointed out to me that the easiest way to remember this is just hydrogen just wants to have fun, okay, which I think is a kind of cute way to remember it, but we've got to remember anytime we have hydrogen attached to fluorine, oxygen, or nitrogen, the electronegativities of these elements are so high that the delta plus and delta minus, the difference in this dipole is quite strong. We're starting to get almost towards an ionic bond, okay? So the electron density is drawn so closely to the nitrogen or fluorine or oxygen that we form a much stronger hydrogen bond. Okay, so this is an intermolecular, an intermolecular hydrogen bond, okay, and it's intermolecular, okay. We're not talking this bond here, okay. This is not a hydrogen bond, okay. We're talking the dashed bonds between the delta plus and the electron cloud of adjacent molecules. Okay, we're not talking the covalent bonds within the molecule itself. It's between adjacent molecules. Okay, so essentially it can occur in any molecule where there is an HF, OH, or NH. Hopefully you can come up with a few examples of these. So HF itself will be hydrofluoric acid, or water will be able to form hydrogen bonds. Ammonia will be able to form hydrogen bonds. Okay, ethanol, CH3CH2OH, it has this hydrogen and oxygen here, so it is also able to form hydrogen bonds. Okay, so we call the hydrogen as a donor, okay, the hydrogen donor, and then the acceptor can be a lone pair or electronegative element. Okay. And again, we represent it with dotted lines, not solid lines. So we can have hydrogen bonds that occur between water, ammonia, hydrogen fluoride, or anything else. Okay. Bit of a bell there for you. Okay, let's move on anyway. So the HF, OH, and NH bonds within molecules are not the hydrogen bonds. We're not talking these ones, okay? We are talking about these dashed lines here. It's one thing that students often confuse, but we're talking between molecules. These are intermolecular forces. Okay, so hydrogen bonds are stronger than all other intermolecular forces. They're the strongest of our intermolecular forces. Okay, so that means that things that have hydrogen bonds form much stronger intermolecular forces and have higher boiling points or melting points. This is incredibly important in biological systems. And if you're doing biology, you may have seen some of these diagrams here where we have alpha helices and beta pleated sheets. These structures and proteins are actually stabilized by hydrogen bonds, as are the way things bind into receptor sites, or even the way that drug molecules interact in our body as well. Okay, hydrogen bonding is the reason why water is so special. Water is a very polar molecule, okay, with partial positive and partial negative charges. And when it slows down, when we take heat out of it and reduce its kinetic energy, it starts to form these hydrogen bond networks, which produce these large hexagonal spaces, which decrease its density. So as it becomes a solid, its density decreases, which actually explains why water floats on top of, ice will float on top of water. It's one of the few substances in the world, or the only one, where its solid is actually less dense than its liquid. Okay, so we have these incredibly strong dipoles in water, and we said we had three types of intermolecular force, which we do. We have dispersion forces, dipole-dipole forces, and hydrogen bonds. The last thing we need to think about is how ionic substances actually dissolve, and this is through ion-dipole interactions. So if you think about it, we have ions, okay, and then we have dipoles. This is the electrostatic attraction between an ion such as Cl- or Na+, and the dipole of water. Okay, so this is what we usually see in solutions of dissolved ionic compounds. We said that the water molecules will surround the ions, which is why they're soluble, okay, and this is what actually happens. The negative anion attracts the partially positive dipole of the water molecule, and then the positive ion attracts the partially negative end of the water molecule. They surround each other, forming hydration spheres, and the salt becomes soluble. This is the way that we can show that. Na solid, in the presence of water, will go to Na aqueous and Cl- aqueous, and then we can show these ion dipole bonds here, which are what actually makes them soluble. Okay, so the water molecules surround, with the positive ends of the water molecules surrounding the Cl- and the negative ends of the water molecules surrounding the Na plus, with the water molecule maintaining its bent configuration. So this is your flow chart of working out how intermolecular forces work. Okay, you look at the interacting molecules or ions. If there's ions involved, okay, are they polar molecules and ions? Yes, then it's going to be ion dipole forces. No, then we're back to ionic bonding. Are there ions involved? No. Polar molecules? Yes, we check for FON, FO and N. If we have FON, then we've got hydrogen bonding. If not, dipole-dipole. If the molecules are non-polar, then the only option we have is dispersion forces. Okay, we've been through that quite quickly. Have a review of this, read your textbook, and remember, have a minimum of 2 questions ready for me for next lesson. Okay, one last thing before we head off. We've defined them all. We need to be able to apply that, and the way we apply that is looking at the effect it has on boiling points. Okay, and if we have a look here, we can see a number of different molecules. Okay, increasing size gives us increasing boiling point because of our larger London forces and dispersion forces. But if we look at things like ammonia, HF and H2O, remembering our FON, these molecules here are all polar and can hydrogen bond. Okay, and we can see that their boiling points are much, much higher. When we go to SH2, no hydrogen bonding is available because we have sulfur and hydrogen, not FO or N. So these are polar, but they're dipole-dipole. Okay, so they're not hydrogen bonding. These are polar, getting larger, going up, but we can see that hydrogen bonding has our greatest influence. These are all non-polar, okay, all non-polar dispersion forces only. They increase with increasing size. These are some examples for you to look through, have a go, and we will talk about them when you get into class and these questions in your textbook as well. So that's it for intermolecular forces. Hopefully it made a bit of sense. Remember, always check, and I'll see you in class.